Hello, and welcome to Chapter 3 of Intro to Psychology. In this video, I will be discussing the neuron at rest. What happens when the neuron is just at rest and there is no neural impulse coming through? So when the neuron is at rest, it is positively charged on the outside and negatively charged on the inside. So you'll see here in this little diagram, in the pink, you have the extracellular matrix, the outside of the neuron. In the blue, you have the inside of the neuron, or the intracellular cytoplasm. And then in the orange, you have the phospholipid bilayer, the cell membrane on both sides, as well as in light orange, the membrane channels or the membrane proteins. And so, as you'll see, denoted by these little symbols, the inside of the neuron is negatively charged, and the outside of the neuron is positively charged. And the neuron maintains this charge because of the concentrations of certain ions inside and outside of the cell. So on the outside of the cell, you have predominantly chloride and sodium ions, and on the inside of the cell, you have mainly potassium ions, as well as a bunch of various negatively charged anions represented by that which keep the inside of the neuron and give it a net negative charge. So there are two forces that act on the ions when the neuron is at rest, two things that control the movement of these ions that we've mentioned. The first one is the concentration gradient. You may have heard it before in other science classes. This is the notion that ions move from areas of high concentration to areas of low concentration. And the movement across the concentration gradient mostly happens via leaky channels. And then secondly, there's the electrical gradient, and that's the principle where opposite charges attract each other and similar charges repel each other. So two positively charged ions will repel each other, whereas a positively charged ion will attract a negatively charged ion. And the movement of those ions largely happens via voltage-gated channels. I strongly recommend taking a look at this website that will be posted to our Canvas page, neuroanatomy.ca. It's a website that's updated regularly by the University of British Columbia and researchers there, and they have some great interactive modules that help explain the basic neurophysiology of the neuron. So I'm going to switch there now. And so to say a little bit more and provide a little bit of a more detailed demonstration of the concentration gradient and the electrical gradient. So once again, the concentration gradient, ions move from areas of high concentration to low concentration. So in this short video, these red ions, because they're so highly concentrated on the inside, they move to the outside down their concentration gradient. And then there's the electrical gradient, which once again follows the principles of opposite charges attracting each other. So in this short video, once the first few positive charges go outside of the cell, the last two positive charges are repelled back inwards because there's a buildup of positive charge on the outside. So these are the two forces that control the ion concentrations in and outside of a neuron. So the major focus of our study of the ions involved in the neural impulse will be on sodium and potassium ions. As you'll see in this diagram, sodium ions are largely concentrated outside of the cell and less so on the inside of a cell. So sodium ions are much more concentrated on the outside of the cell, keeping it with a positive charge on the outside. The reverse is true for potassium ions. Potassium ions are much more strongly concentrated on the inside of the cell and less so on the outside of the cell. So even though potassium is highly concentrated on the inside, remember that there are other anions that keep the inside of the cell and give it a generally net negative charge. For the sake of understanding the concepts in this lecture, it might be easier just to remember that potassium is most strongly concentrated on the inside of the cell, and sodium is most strongly concentrated on the outside of the cell. I'm going to skip to part 2.4. So, the next important concept is the resting membrane potential. So, the movement of potassium and sodium ions really determines whether or not the nerve impulse will be able to propagate along the axon. And that is largely determined by this resting membrane potential of 70 millivolts, negative 70 millivolts. So, when the neuron is at rest, the membrane stays at a charge of negative 70 millivolts. And once a signal comes through, it's the activity and movement of the sodium and potassium ions that causes that resting membrane potential to change. Two more terms that are important for us to know, in addition to the resting membrane potential, are the terms depolarization and hyperpolarization, as well as we'll discover later, repolarization. So, when the neuron is at rest and it is at a resting membrane potential of negative 70 millivolts, when a signal comes through, it is depolarized. It becomes more positive. When you hear the word depolarized, think more positive. The membrane becomes more positive. And that is considered to be an excitatory event. So when the signal is coming through, when a neuron is being activated, when we say that your brain is sending signals, we're talking about depolarization that is happening along axons. And then there's also hyperpolarization, which is an inhibitory event. And that's where a signal is being blocked or a signal is being stopped, and that's caused by certain movements of the potassium and sodium ions reaching a threshold where it blocks the transmission of the signal. So I'm going to switch back over. And so in the next video, we're going to talk a little bit more about the transmission of a neural impulse within a neuron. What happens, what chemical changes occur that allow the signal to be propagated down the axon.